Mathematics for grade 10, real numbers. In this video, we shall learn the Euclid's division lemma and Euclid's division algorithm. These two things, namely Euclid's division lemma and Euclid's division algorithm, are very closely interlinked, so that many times people use these two things interchangeably. But what does Euclid's division lemma actually state? The division lemma by Euclid states that any positive integer a can be divided by another positive integer b in such a manner that it leaves a remainder r which is always smaller than b. Now let's state this Euclid's division lemma in a more formal manner in form of theorem 1.1 of the textbook, which states that Euclid's division lemma is: for a given positive integer a and b, there exist unique integers q and r which satisfy these two conditions, which are a is equal to b times q plus r, the remainder, and r is between 0 and 1, 0 and b, and r can be 0, that is 0 is less than or equal to r and r is less than b. Two things should be noted here, that both q or r can be 0. They can be 0 simultaneously as well. If both q and r are 0, then as per this equation a will be 0 as well. The other thing to note is that for a given a and b, the values of q and r are unique. That is, for the given a and b, the q and r are the only integers which satisfy the conditions a is equal to b times q plus r and 0 is less than or equal to r and r is less than b. In summary, we can say that r is greater than or equal to 0 and r is smaller than b is the Euclid's lemma. Before we go to the Euclid's division algorithm, let's try to differentiate between an algorithm and a lemma. Algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Or in other words, algorithm can be a well-defined set of steps or procedures which yields an output or a result or solves a given problem. Lemma, on the other hand, is an already proven statement which is used for proving another statement. So lemma is a proved statement which is being used for proving something else. Now we go to Euclid's division algorithm. Note that this is algorithm here, so it will have some steps. So in case of Euclid's division algorithm, we have these steps. And what does Euclid's division algorithm state? It states that to get the H.C.F, the highest common factor, of any two positive integers, say c and d, where c is greater than d, we can follow these steps. Step 1 is apply Euclid's division lemma to c and d to find the whole numbers q and r such that c is equal to d times q plus r and 0 is less than or equal to r and r is less than d. The step 2 is, if the remainder is r is equal to 0, then d will be the H.C.F of c and d. But if r is not equal to 0, then we will apply the division lemma again to d and r. So these two are different. Earlier we applied the lemma to c and d, but now we shall apply them to d and r. So the step 3 will be, that is to continue the process until the remainder is 0, and that is when r is equal to 0, and then at that time when the r is equal to 0, the divisor at that time will be the required H.C.F. And just to refresh your memory, we can say that H.C.F of two positive integers a and b is the largest meaning the highest, and the word h in H.C.F is highest. So the largest positive integer d that divides both a and d. So H.C.F of two numbers a and b is the highest integer d, which divides both a and b. Now let's do some examples. This is example 1 from the textbook, and it asks us that use the Euclid's algorithm to find the HCF of 4052 and 12576. So let's take the first steps to solve this, and we notice that 12576 is bigger than 4052, so we shall keep this 12576 in the dividend position, and let's apply the lemma to these two numbers, and we obtain an equation like this. So we have 12576 is equal to 4052 times 3 plus 420. So we notice that this equation has remainder of 420, and this remainder of 420 is not equal to 0, so we shall continue to apply the lemma again. And when we apply lemma, now the numbers will change. The 420, which is a remainder here, will become the divisor here, and 4052, which is the divisor here, will become the divisor, will 4052 will become the dividend here. So we apply the lemma again, we get the remainder 272. So the remainder 272 is still not 0, so we shall apply the lemma again to the numbers 420 and 272. 272 comes from here, this was the remainder, 420 is the divisor, and current divisor 420 will become the dividend here, and the remainder for 272 will be the divider, the new divider. When we do this, we get a remainder of 148. This 148 is still not 0, so we apply the lemma again. We get the remainder 124, divisor here is 148, but the remainder is still not 0, so we apply it again, and we get the equation 148 is equal to 124 times 1 plus 24. 24 is the remainder, which is still not 0, so let's continue this process once again. So we get 124 is equal to 24 times 5 plus 4, so the remainder is 4, which is still not 0, so let's apply the lemma once again. So we get 24 is equal to 4 times 6 plus 0. So now you see this time the remainder is 0, and therefore our procedure will stop. Now you see the divisor in this last equation is 4, and this 4 by the algorithm by Euclid we will say will be the HCF of 12,576 and 4,058. You will notice that the 4 is HCF of other pairs in these equations as well. And let me change the ink color to highlight that 4 will be the HCF of 24 and 4, which is, if you see here, 24 and 4. 4 will also be the HCF of 124 and 24, which is 124 and 24. 4 will also be the HCF of 148 and 124, which is 148 and 124, and so on. So if you see in all the combinations of C and D above in the form here, like 272 and 148, 4 will be their HCF as well. So we have solved this example, and we have found the HCF of 12,576 and 4,052 as the number 4. Let's now get to the example number 2, which is to show that every positive even integer is of the form 2q, and every positive odd integer is of the form 2q plus 1, where q is some integer. So to start solving it, let us assume a to be any positive integer and let b is equal to 2. Now using Euclid's lemma, we can write a as equal to 2 times q plus r. So if you notice in our case, b is 2 and we have a is equal to b times q plus r. And in this case, q is some integer greater than 0. So we have taken q to be basically greater than or equal to 0. And r is the remainder, is some integer which is greater than or equal to 0 and is less than 2. That is, r is either equal to 0 or r is equal to 1. Because as per lemma, the r will have to be smaller than the number 2. So we have this r as either equal to 0 or this r is equal to 1. So when this r is equal to 0, we have a becoming equal to 2q, and when then r is equal to 1, in here we get a is equal to 2q plus 1, because we put the value of r is equal to 1 here, so we get 2q plus 1, which is nothing but a is equal to 2q plus 1, and when r is equal to 0, we put r is equal to 0 here, and we get this value as a is equal to 2q. So if a is of the form 2q, then a is an even integer, because any even integer is divisible by 2 and this is divisible by 2. Similarly, we can say a positive integer can be either even or odd, so we have any positive odd integer is of the form 2q plus 1. So we have solved this example as well. Let's go to the third example, which is show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. So let's suppose a is a positive and also an odd integer. We apply Euclid's division algorithm with the a and the number 4, and the equation will look like this. A is equal to 4 times q plus r. Now the lemma states that the remainder r has to be between 4 and 0, that is 0 is less than or equal to r and r is less than 4. So this implies that the values that r, the remainder, can get is either 0 or 1 or 2 or 3. So now let's place all these values of r into our equation here. Okay, so we can get a will be equal to 4q when r is equal to 0. Similarly, a will be equal to 4q plus 1 if r is equal to 1. Similarly, when r is equal to 2, the value of a will be 4q plus 2. When r is equal to 3, value of a, that is this, will be 4q plus 3. Now we have already assumed that a is an odd number. We had assumed it here to be an odd integer. So we can say that our well a cannot be 4q or 4q plus 2, because both these 4q plus 2 and q can be divided by 2. So we basically can easily rule out equation 1. So this equation 1 is ruled out, and similarly equation number 3 is basically ruled out. So a cannot be this and a cannot be this. So we are left with that a, which is an odd integer, is either equal to 4q plus 1, which is this, or it is equal to 4q plus 3, which is this. And hence we have solved what is asked of us in this example number 3. Let's do one more example, and this will be the last in our video. Example 4 is from the textbook. It states, a sweet seller has 420 kaju barfis, which is a kind of a sweet, and she also has 130 badam barfis, a different kind of sweet. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. So we have to find out what is the number of the barfis, that is those sweets, that can be placed in each stack for this purpose. In lower grades or classes, we would have solved this problem by trial and error method, but in this case we will solve the problem more systematically, that is by finding the H.C.F of the given two numbers 420 and 130. So if we find the HCF of these two numbers, we shall get our answer, because that will be the number that we can stack, number of burpees that we can stack when the area of the tray used will be the least. So our problem is to solve and get the HCF of 420 and 130. The first step is 420, which is the bigger number, we keep it on the left hand side, and the 130, which is the other number, is the divisor, multiply by 3, and we get 30 as the remainder, R. So this R30 is not 0, so we continue to the next step, and the next step is we move the divisor to the dividend position. 130 is here, is equal to 30 is the remainder from the previous step, and we get 10 as a remainder in this step. This 10 is again not 0, so we will have to solve this one more step at least. So we place 30 here, 10 the previous remainder here, and 3 is the multiplier this time, and 0 is the remainder this time. So now that we have hit 0, the divisor in our case is 10, will be the HCF, and hence the answer. So HCF of 420 and 130 is 10, and we can say that the sweet seller can make the stack of 10 of both kinds of burpees, and that is the answer for our example number 4.